The hysteresis of ferromagnetic materials represent the phenomenon of lagging of magnetization behind the applied magnetic field. It is an irreversible characteristic. So characteristics are as follows. When the magnetic field is applied on the ferromagnetic materials, the magnetization increase rapidly with applied field up to a value of after the remains constant. This magnetization called saturation of magnetization. And this is second property. If magnetic field on the material is reduced back to zero, magnetization will not travel in that initial path, creates new path, and it reaches to a point called residual magnetization, called as a retentivity. Okay. Next property. Reduce the residual of magnetization to zero. Negative field has to be applied. When sufficient negative field applied, then the residual magnetization becomes zero and the field is known as a negative coercive force. Further, if negative magnetic field is applied, then it increases the magnetization is negative in the direction, and this is magnetization in a negative direction, so called as a negative saturation of magnetization. Next, if the negative field is decreased back to zero, the negative saturation of magnetization will not be traveled in the initial path, creates a new path and reaches to a point called as a negative residual magnetization, and this is called as also called negativity retentivity. Okay. So next property, decrease the negative residual magnetization to be zero. There some positive fields has to be applied, the amount of magnetic field required to bring residual magnetization to zero. Next property, increase of positive magnetic field, the magnetization reaches again to positive saturation, and it is cyclic process. Delta Q equals to 0. In the above mechanism, this is the show that hysteresis curve. Okay, so this is an important of the exam view. Okay, figure shows that should be observed that the magnetization vector which is started from origin will not reach back to that point, hence it is an irreversible property, and the magnetization always lags behind the magnetic field applied. The area of hysteresis loop refers to the hysteresis loss. If the loop area of ferromagnetic material is large, then more loss of accuracy during each cycle of hysteresis. On her hand, if loop area is less, then dielectric loss will be less. Okay. Next property. So hysteresis loss values, they are classified into two categories, and they have two types of materials: soft magnetic materials and also hard magnetic materials. So first, soft magnetic material. So there are soft magnetic materials are easily magnetized and also demagnetized, are known as soft magnetic materials. These are the salient features. Soft magnetic materials main features of the soft magnetic materials are hysteresis loop area is less, hence hysteresis loss is less. Area is less, hysteresis loss is less. So their properties are permeability and susceptibility are large, eddy current loss is more due to high resistivity. Coercivity and retentivity are small. Magnetostatic energy is very small. It is used in electromagnetic mechanism and transformers, such as the examples of ferrites and garnets. So next material, hard magnetic material. The magnetic materials cannot be easily magnetized or demagnetized, also known as hard magnetic materials. And this is the property of hard magnetic materials, that is, hysteresis loop area is more. Hence hysteresis loss is more. Permeability and susceptibility are small. Eddy currents loss is less due to smaller resistivity. Coercivity and retentivity are large. Magnetostatic energy is large, and its use in making magnets, magnetic detectors, microphones, magnetic repeaters, etc. etc. So this is the curve. Point of exam you, this is more important. So this is a, remember that. Some examples of hard magnetic materials: plain carbon steel, cobalt steel, aluminum, nickel, cobalt alloy. Domain theory of ferromagnetism. This is a theory of ferromagnetism. The domain structure is one of the important characteristics of ferromagnetic materials. The magnetic moments of all the atoms in domain are aligned in a particular direction, but different domains are oriented in different directions, such that the net magnetization of material is 0. The size of domain varies 10 raised to minus 6 meter to the entire volume of the crystal. According to domain theory, it's that the domains arise to minimize the energy of material. So, ferromagnetic materials possessing the domain structure which of the total internal energy is minimum. The total energy of the domain structure ferromagnetic is minimum because of this is a type of magnetostatic energy, magnetic field energy, or exchange energy. Second one, crystalline energy and anisotropy energy. Domain wall energy, the block wall energy, and magnetostriction energy. So see the one by one. So first, magnetostatic energy or magnetic field energy, or also the exchange theory, the interaction energy which makes the adjacent dipoles align themselves, known as the exchange energy. This is the basic definition, or as well as is called as a magnetic field energy. It is the energy required in assembling atomic magnets into a single domain, and this work done is stored as a potential energy in the field outside. This is the main equation, 1 upon 8 pi integration of h square dv. So the magnetic field energy has been reduced by 1/2 as a result of dividing the crystal into two domains magnetized in opposite directions. The subdivisions can be continued until the reduction in magnetic energy is less than the energy domain and its boundary called block wall. So the figure 8.10, see that 8.10. So because the normal component of the magnetization is crossing the each domain boundary is continuous, that is, there are no free poles, and therefore there is no field energy. In order to obtain the energy, minimum magnetic field energy, the ferromagnetic materials exhibit closer domain in structure. So there are structures of magnetic field. Spin are opposite direction. So next, crystalline energy or anisotropy energy. It is experimentally found field energy required for saturation magnetization in ferromagnetic materials depends on the direction of magnetization. Dependency of direction of magnetization. Example, BCC structure, BCCIR, HKL 100 and medium direction 110 HKL and hard direction, that is 111 symmetry. That is, in order to produce the same saturation magnetization, the energy required in the hard direction is a more than energy required in easy direction. Okay. So basic definition: the excess of energy required to magnetize a specimen in a particular direction over that required to magnetize it along the easy direction is called as a crystalline anisotropy energy. So the magnetic dipole align along the easy direction so that anisotropic energy is minimum.